Greetings again, everyone. I've got a bonus video for you right now. I've made two more example problems for you. The first one is going to be a perfectly inelastic collision with no numbers, only variables. I know how much you love that. And the next one is going to be an inelastic collision, not a perfectly inelastic collision, and just a regular inelastic collision with a truck rear-ending a car. First things first, let's do an example problem where we've got two masses, and I will label them as M1 and M2, and they collide. M2, we're going to have V initial be 0 meters per second, but V for the first one, for M1, I'm going to let that just be V1 initial, and I'm not going to say what it is. We're going to have this being completely arbitrary. And we need to figure out some sort of function for the final velocity if the collision is perfectly inelastic, meaning if they bounce into each other and stick together, what is going to be the final velocity? So this is for a perfectly inelastic collision. Okay, well, we know that because this is a collision problem, we're going to definitely have to use conservation of momentum. So delta P is equal to 0, P initial is equal to P final. Well, my initial momentum is going to be the initial momentum of object 1 plus the initial momentum of object 2, and my final momentum is going to be the final momentum of object 1 plus the final momentum of object 2. And I can say P initial 1 plus P initial 2 is equal to P final 1 plus P final 2. And M2 is stationary at the beginning, meaning it has no momentum because it has no initial velocity. And then we can plug in our equations that momentum is equal to mv, of course. And so we've got mass of 1, velocity initial 1 is equal to mass 1, velocity final 1, plus mass 2, velocity final 2. Because it's a perfectly inelastic collision, they're going to have the same final velocity. So V final 1 is equal to V final 2, and I'm just going to call that V final, like I did here. We can plug all that in. We've got M1 V initial 1 is equal to M1 V final plus M2 V final. M1 V1 initial is equal to V final, M1 plus M2, algebra, V final is equal to M1 V initial 1 over M1 plus M2. If the two stick together, then this should be the final velocity. If one of them started at 0 and one of them was moving at some initial velocity 1, then really you can just plug it into this. I do not recommend that you memorize this equation. This was easy to come up with. I showed every little step in this entire thing, and it did not take very long. So don't just memorize this equation. Be able to recreate this equation. It is so much easier to be able to recreate the equations than just memorize. If you have to memorize this, you'll never see this exact question on any test, so knowing how to get there is far more important. Let's test to see if it makes sense. Well, if the initial mass of, if the mass of the moving object is a lot, or if the velocity of the moving object is a lot, then we expect a large final velocity. That makes sense. High numerator means high final answer. If M2 is a whole lot more than M1, then this numerator isn't going to be very much compared to M2, and that M1 isn't going to be very much compared to M2. So if this is absolutely tremendous, then you get very low final velocity. If m1 is very, very large compared to m2, then this m2 doesn't really matter. And it's mostly just m1 v1 over m1. And so if m2 is very, very small, then we can kind of consider it to go away, it's approximately gone away, and you're just going to have m1 times v1 initial over m1, and those will also cancel, and you'll get that the final velocity is almost the same as the initial velocity if m2 is very small and m1 is very large. All that makes sense from an intuitive perspective, that if the mass of the second one is just like a snowflake, and that's a bowling ball, then the bowling ball isn't going to slow down very much. Whereas if that's the bowling ball and that's the snowflake, then the snowflake is just going to hit it and stop. And so that makes sense given our equation here and given our intuition when we just think about the problem itself. Here's the next example problem that I wanted to give you. This is from one of my old tests, so you won't find it in the files section. The question is, a car, mass 1,200 kilograms, velocity 25 meters per second north, is rear-ended by a truck. So here's our car, here's our truck. It's going to get rear-ended by the truck. So the car's already moving forward and the truck rear-ends it. The truck has a mass of 1,800 kilograms and a velocity of 35 meters per second north. Immediately after the collision, the truck is traveling at 29 meters per second north. We need to find the velocity of the car after the collision. We already have the velocity of the truck after the collision. All we need to do is figure out the velocity of the car after the collision. A good idea before you start any collision problem is to try to figure out what kind of collision it is. Well, if it's an elastic collision, all the energy is conserved, and the vehicle will probably be bounding off at a very, very high speed after that collision. If it's a perfectly inelastic collision, they will connect together and move on together after that. In an inelastic collision, it's halfway in between, that they will bounce off of each other, but they won't conserve all their energy. This one is actually very difficult to tell what it's going to be, but we have been given a lot of numbers for this. So sometimes we can't figure out what kind of collision it is from the beginning. Sometimes we actually need to do the math and figure out what kind of collision it is from that. So let's just go ahead and do the math. Well, this is a collision problem, and in every single collision problem we're ever going to do, we're going to conserve the momentum. So delta P is equal to 0, P initial is equal to P final. And this is going to indicate that the momentum initial is the momentum initial of the car plus the momentum initial of the truck. Momentum final is momentum final car plus momentum final truck. And we can say momentum initial car plus momentum initial truck is equal to momentum final car plus momentum final truck. Mass car, velocity initial car, plus mass truck, velocity initial truck, is equal to mass car, velocity final car, plus mass truck, velocity final truck. You see how ridiculous this gets. It's growing exponentially, just like a certain virus that I'm not going to name. Just more and more stuff going down this. It's going to get even worse when we start having collisions take place in multiple dimensions, where you have this kind of thing. It's going to get twice as bad, actually. So just be prepared for that. So, do we have these numbers? Well, actually, yeah, we have effectively all these numbers. Mass of the car, 1,200. Velocity initial of the car, 25. Plus mass of the truck, 1,800. Velocity initial of the truck, 35. Mass of the car, 1,200. Velocity final car is the thing that we're looking for. Mass of the truck, 1,800. Velocity final of the truck, 29. Well, this is just algebra. Multiply add multiply equals the thing plus multiply, you can do that. We're not going to waste our time actually solving that. I already solved it over here. You can probably see my math right there. And you see that when you take the stuff on the left, the other stuff on the right, subtract them, divide by the mass, you get V final car is 34 meters per second north. This is another easy, quick one. If this one or the previous one with the perfectly inelastic collision where we just solved it using variables, if either one of these was confusing for you, please tell me. These are very basic problems, and so if this is giving you a challenge, then you definitely need to talk to me. I'll be available for office hours, or you can email me, and we will discuss this stuff. So, until next time. Alright, next time ends up being right now because I wanted to mention that this ends up being an inelastic collision. This is an inelastic collision. You can kind of tell that because, well, they certainly don't stick together. The truck was traveling at the end at 29 meters per second north, whereas the car is going at 34 meters per second north. So they definitely didn't stick together if they're going at different velocities. And you can always calculate to see if energy was conserved. In this case, energy is not going to be conserved. And I'll leave that to you to actually calculate, but you can always try it out by seeing whether or not E final is equal to E initial. I don't know if they're equal to each other, but this would just be kinetic energy of the car final plus kinetic energy of the truck final. Does that equal kinetic energy of the car initial plus kinetic energy of the truck initial? Well, we can plug in all the equations for this, plug in all the numbers for this, and you will see that they are not equal. So that's another good exercise for you to get a little bit more practice and in looking back at energy in particular. But calculate, confirm that energy is not conserved in this problem. And so, next time we will be continuing on with momentum and doing a few more example problems with it. And so until next time, have fun and good luck. Email me if you need any help.